Good morning and welcome to NASA Langley Research Center. My name is Adeline Deinhardt and I'm an education specialist here in NASA Langley's Office of STEM Engagement. Today is a big and exciting day for all of us here at NASA and hopefully for you too, as we prepare for Mars InSight's landing on Mars later this afternoon. Today we have two guest speakers with us who are going to share with you all about Mars InSight. We'll have a short Q&A where you can ask some questions, and we'll also answer some of the questions we got during pre-registration. We'll then continue on to do a short classroom activity. Now, don't forget to be sending your questions in through the chat feature, and we'll answer as many as we have time for. Now let's get started. Sam Duda is an aerospace engineer in the Atmospheric Flight and Entry Systems branch at NASA Langley Research Center. His current research focus is a flight mechanics simulation and modeling of planetary entry systems. Sam has a PhD and MS in aerospace engineering from the Georgia Institute of Technology and a bachelor's in mechanical engineering from the University of Tennessee, Knoxville. He is currently supporting Mars 2020 and InSight missions, and he has worked on supersonic parachute tests like LDSD and Aspire, and entry technology tests like Adapt Deployable Heat Shield. Michelle is the EDL System Capability Lead for NASA. She has worked on EDL technology development for over 15 years, and she has supported the Mars Odyssey operations and the MEDLI instrument on the Mars Science Laboratory. Ms. Monk has a BS in Aerospace Engineering from Virginia Tech. Now I'm going to turn it over to them and let them tell you a little bit more about Mars InSight.
Good morning, everybody.
Good morning. And I guess this is a pretty exciting day for us, both been involved in a lot of Mars missions over the years, and to see something land on another planet is a extremely exciting day for us.
Does not happen every day.
Nope. And both of us have served a little bit of a role on this mission, and so we're excited to see what our colleagues and we have been able to do today. Today's the test.
That's right. So I look over all the entry, descent, and landing technologies and missions that we have going on all across NASA. So I've been involved a little bit in all of them. Sam here and a lot of our colleagues here at NASA Langley, where we're located, have really contributed to Mars InSight. At NASA Langley, we're the ones like Sam and the rest of the team who work on the trajectory simulation. So we actually generate the landing footprint and decide whether it's safe for the system to land or not, and where it will end up. So we're always very excited to see how we did compared to the footprint that we predicted.
And we'll have some imagery in a few minutes to kind of explain what a landing footprint is, in case those of you are wondering what that means. But yeah, we have a few slides here to talk to you about InSight and Mars in general. So if you can roll with that. Oh. So we'll start with an image of Mars in general. You guys are all familiar with the red planet, hopefully, since you guys are landing in. And we'll talk about where we're landing with InSight on Mars in a few slides here. But at first, let's talk about what entry, descent, and landing is, because that's what both Michelle and I do.
The most critical part after launch, of course.
And they call it the 7 minutes of terror, and you will hear why.
Although we've done it before, landing on Mars is hard, and this mission is no different. The process to get from the top of the atmosphere of Mars to the surface, we call entry, descent, and landing, or EDL. It takes thousands of steps to go from the top of the atmosphere to the surface, and each one of them has to work perfectly to be a successful mission. The process starts well above the top of the atmosphere of Mars. The cruise stage faces the sun. It also has its radio antenna, which faces Earth. But now we don't need the cruise stage. Its job is done. The next step, just 7 minutes before arriving to the top of the Mars atmosphere, is to separate the cruise stage. Before you hit the top of the atmosphere, though, the space capsule has to orient itself so that the heat shield is precisely facing the atmosphere. Now the fun begins. The vehicle is moving at nearly 13,000 miles an hour, but it's hitting the top of the atmosphere at a very shallow angle, 12 degrees. Any steeper, the vehicle will hit the thicker part of the atmosphere and will melt and burn up. Any shallower, the vehicle will bounce off the atmosphere of Mars. At the very top of the atmosphere, it's about 70 miles above the surface of Mars, and the air is starting to get thicker and thicker and thicker. As it does that, the temperature of the heat shield gets well over 1,000 degrees centigrade, enough to melt steel. Over the next 2 minutes, the vehicle decelerates at a backbreaking 12 Earth Gs, from 13,000 miles an hour to about 1,000 miles an hour. At about 10 miles above the surface of Mars, a supersonic parachute is launched out of the back of the vehicle. 15 seconds after the parachute inflates, it's time to get rid of the heat shield. 6 pyrotechnic devices fire simultaneously, allowing the heat shield to fall and tumble away from the vehicle, exposing the lander to the surface of Mars. 10 seconds after the heat shield is dropped, 3 pyrotechnically deployed legs are released and locked for landing. About a minute later, the landing radar is turned on, sending pulses toward the surface of Mars as the vehicle starts to try to measure how high it is above the surface and how fast it's going. At about a mile above the surface of Mars, the lander falls away from the back shell and lights its engines. And very quickly, the vehicle must rotate out of the way so that the parachute and the back shell doesn't come down to hit it. The last thing that has to happen is that on the moment of contact, the engines have to shut down immediately. If they don't, the vehicle will tip over. So if all the steps of entry, descent, and landing happen perfectly and we are safely on the surface of Mars, we'll be ready to do some exciting new science.
And that's why they call it the 7 minutes of terror.
Yeah, all those steps that Rob Manning was talking about, they're choreographed and we rehearse it many, many times. Now, of course, we can't really test it on Earth by firing the whole system every time. So we test it multiple times in what we call flight simulations. And that's kind of my day job. I design trajectories on different planets. When I come in the morning, I have to think, okay, which planet am I designing trajectories for today? And thankfully, it has been Mars a lot. And so let me go to the next slide. This is a terrain of Mars, and you could see that this is from a website called Mars Trek. You're welcome to go take a look at that. It has some very high quality images of Mars. And we're landing InSight in this little gray patch that you see here. That gray patch is from the HiRISE camera, which is on board a orbiter called the Mars Reconnaissance Orbiter, MRO. And we take these high definition pictures, high-res pictures, so that we can see what kind of rocks we're landing on and basically to avoid it. And InSight is, as you saw in the entry descent landing video just a few minutes ago, InSight basically has, once it comes off the parachute, it's has engines on and kind of lands slowly over a location. It doesn't try to avoid rocks. So we have to make sure that we put it in areas which is pretty safe. So this area you can kind of see doesn't have that many large craters. It's pretty flat looking. And if we go to the next slide, you'll see what Michelle was talking about before was landing footprints. So footprints are our predictions of where things are going to land on Mars. And we usually go ahead and draw an ellipse around them to kind of show 99% of chance that we're going to land within this location. There's always a little bit percentage of chance that we can land outside of it, but 99% of the time we try to make sure that we're landing within it. So in this particular slide, this is just one trajectory that we looked at. I'm not saying that this is what InSight's going to land today, but you can see that the ellipse is as large as 87 kilometers by 25 kilometers. So that's 87 kilometers in the lengthwise and 25 kilometers in the widthwise. So that's that means that ellipse InSight is covering a lot of ground. And these ellipses are generated from our simulations, where we try to capture all the physics that goes into that entry, descent, and landing portion. So we're talking about the aerodynamics, the atmosphere, the different masses that we're ejecting at different time, how the thrusters are working, how the flight software is working. We simulate all that. And then not only do we simulate it that once, we simulate that 8,000 times so that we generate enough statistics so that we can come up with things like the landing footprint. And Michelle, you were saying that we like to kind of test ourselves later on to see how well we did here.
Right. I mean, the really interesting thing is that we don't really know precisely where we are when we get to Mars. We don't precisely know where Mars is and all those other factors that you talked about. So all of that is simulated with mathematical equations. And I think the statistics part is really fascinating as well. But that's why, you know, we don't just have one point where we're landing. There's this whole range of places we could land depending on which combination of things we don't quite know actually happen. So this is a really important part of everywhere from designing the vehicle from day one all the way to picking the landing site and then actually making sure that the landing site is safe. Rob talked about the landing radar, and you said, you know, we're landing in a safe place with InSight so that because we don't have the capability to move the lander away from any rocks. In the future, when we start landing things close to each other to send humans to Mars, we're going to have to land several things very close together so that they can use all the resources. We're going to have precise landing. So that's one of the technologies that we're working on for the future is to better sense the surface and be able to move the lander away from a hazard like a rock or a crater or another lander so that we can make sure everything stays safe and usable.
You don't want the cargo ship coming down and sandblasting the human habitat, for example.
That's right.
You want to avoid that. And actually, going back on what you were saying, the ellipse of InSight is 86 kilometers wide. That's a pretty large area. What kind of ellipse sizes are we looking at for human missions?
We are trying to land precisely in a 100-meter circle. So, and that is because, as you mentioned, sandblasting. When we land with engines, particularly like InSight's engines or like the ones we're going to use for human landers, those engine plumes are kicking up regolith and soil and
it's Mars dust.
Big rocks. Yep. And we want to be careful not to spray our other landers with that debris. So that's one of the really interesting things on InSight. It's landing on very deep soil, essentially. If anybody remembers when Phoenix landed and showed us that one picture from the underneath the lander and we could see ice and it kind of blew the dust away and we could see the ice, that was what we call bedrock. And InSight will not land on bedrock. And so this is a really good opportunity for us to look at how the engines move all the soil away and use the camera after landing to look at the crater that we formed and then use that in our computer predictions to see how that soil might behave on future missions. So that's one of the extra bonuses we're getting from InSight.
So we both work at Langley Research Center. Of course, this missions like this, like InSight and Phoenix that Michelle talked about, take a lot of different centers to work at. But here at Langley, we specialize in a few areas of entry, descent, and landing. We specialize in being able to give flight simulation predictions of EDL, but we also specialize in the aerodynamics of the vehicle. So we try to make sure that we know what kind of forces and moments are acting on the vehicle. That's good to keep track of to make sure things don't tip over or you don't put too much force on the vehicle where something breaks structurally. So one of the tests we did for InSight specifically at Langley was a static wind tunnel test, meaning that the vehicle was not moving around, it was static. And we wanted to see what happens to the aerodynamics when the solar arrays on the vehicle, you could kind of see the solar arrays here, and the circular solar arrays. They're almost the same size as the lander themselves. When they get deployed about 30 minutes after the vehicle lands, we wanted to make sure that the vehicle doesn't tip over or blow away if the aerodynamics of the if a wind event kicks up or something like that. So that's one of the things we tested to make sure that that doesn't happen. We saw up to what kind of wind speeds we needed to have that happen and make sure that we're not landing in seasons where we see that kind of wind speeds, and then tested them also with normal wind speeds that we are going to see and made sure that things were aligned properly. And so actually we have another picture here to show you kind of the test setup. It's a very simple test setup, but the point is sometimes simple tests give you a lot of important information. So this was a test that was done in 2016. They did a similar test for the 2008 Phoenix lander. Now, if you guys are watching about InSight, I hope you have read a little bit about Phoenix itself. Mars Phoenix landed about 10 years ago on Mars, and it looks very much similar to InSight in a lot of the technologies. Actually, you were part of the initial proposal review committee for InSight, right?
Yeah, so InSight was actually chosen as a discovery mission out of about 30 missions back in 2012. So it was first proposed in 2010, finally selected in 2012, and it was supposed to actually launch in 2016. And the reason why it was so quick, 4 years to make a Mars mission is very fast, because you can see how complex this is. We had a difficulty in one of the main instruments, so we needed to delay the launch, and the alignments of Earth and Mars only happen every 26 months so that we can easily go there with the least amount of fuel. So we had to wait, we couldn't just wait a couple months. We had to wait a whole, 26 months. So that's why we launched earlier in 2018 on May 5th, and took about 7 months to get there. And so here we are at landing day finally.
And InSight's landing actually pretty quickly compared to the date of its launch. I think other missions take a little bit longer. So that's actually something unique about InSight itself.
Right. It may be because it's a smaller lander, so the smaller mass you're throwing on the rocket towards Mars, the more thrust you can give it, and it can go on a little faster trajectory.
Well, yeah, and actually the Atlas V rocket that they had good capability on it, and that's another reason they actually launched it out of the west coast of United States. Typically, you probably have seen most launches occur from Kennedy Space Center on the east coast, but as you said, InSight's small enough, and the launch vehicle had good capability. They could not only send it fast, but they could also launch it from a launch center that wasn't that had enough energy to launch from the west coast instead of the east coast of United States.
Back to this wind tunnel test, I thought this was just super cool because usually we only get to test the capsule configuration like Rob showed on the screen. The blunt body, which we've used since the 1970s when we sent the first Viking landers to Mars. We've always used that same shape, but we still have some uncertainties about how it flies and depending on what we're packaging inside. So you kind of always see the same sort of wind tunnel test models, but it was really unique for us to test InSight in its landed configuration. Took me back to the Martian opening scene where there's a windstorm, a dust storm that is almost going to blow over the ascent vehicle, and we were kind of testing the same thing here for InSight.
Yeah, and it's good that we did test it because earlier this year we had that global dust storm on Mars, so they had to. Good thing that we have data now to kind of look at what would happen.
That's right.
And I think we have a little bit more pictures here before of the wind tunnels. You can kind of see things, the solar arrays at different angles and what that would create. We basically have force measurements that we're taking of the vehicle just to make sure that we understand what are the forces and then moments, tipping moments on the vehicle as we go through here. And I think you just kind of see, it's a very simple configuration, but that's kind of the point. We don't always have to test it at the most sophisticated wind tunnels to get actual data that's helpful for our landing. And by the way, the main reason we didn't test InSight as much in wind tunnels was because Phoenix actually went 10 years ahead, so we had a lot of the data for it. But just to kind of give you guys an idea that it's not, even though you can do some simple tests, you could see the flow visualization here of the basically what's happening to the aerodynamics or what's happening to this wind that's hitting this vehicle. So you can see little eddies swirling out of here, which, you know, we're
That's
recording.
really cool.
Yeah. And I guess yet another good picture of that. So now we're getting into looking at how we put everything together. So Michelle mentioned that my job has been, since I started here at NASA 5 years ago, to do flight mechanics analysis. That's basically raw numbers of predicting what the trajectory looks like over time. But we also like to visualize it so that we can see if the vehicle's acting the way we think it's supposed to act. So here is an example of such an animation. It's a simple animation. It's what we engineers use to look at how the vehicles are looking at. So it's not as splashy as, you know, a final production grade video would be. But this is, again, something we created here at Langley. And this is typically what we look at on our meetings to understand what's happening. So if we can go ahead and play that.
Much easier to communicate with your bosses this way.
Okay. And it's slow initially because you know, we're at cruise state separation. Oh, actually, we haven't even gotten to the cruise state separation. But you can slowly see Mars changing here, and we'll kind of skip around here a little bit. The vehicle goes through different configurations, as you know, and then here we are. We have separated from the cruise stage. We're actually getting into entry, and you can see the little thrusters firing so that we can orient ourselves correctly as we enter the Martian atmosphere. And this is slew to entry attitude. Now we're already in hypersonic flow, so that's faster, 5 times faster than the speed of sound. That's speed at least 5 times faster. This is actually probably even more like Mach 10. So then we're going to get into parachute. That's not going to be, that's about Mach 2, and you could see a little bit less than Mach 2. Parachute comes out, the legs come out, and now the back shell will get ejected with the parachute and will come down in the landing configuration. And this video has been sped up a little bit. As I said, this is 7 minutes of terror, and we didn't want you to be here to see 7 minutes of it, but please read up a little bit more on entry, descent, and landing and the 7 minutes of terror on nasa.gov. You'll find more resources about it. But here we are in the terminal descent phase. We're turning on our engines, and we have touched down. And InSight has landed. And about 30 minutes after landing, the solar arrays deploy and the missions start.
Yeah, that's really important to get those solar arrays out as soon as possible, because those collect the sunlight to charge the batteries so that InSight can last through the nighttime. And that's one of the reasons why InSight lands so close to the equator, right, Sam?
Yeah, that's part of making sure that we have enough energy to do all of our to power all of our science instruments, and we have quite a lot of science instruments on board InSight as well, because we're trying to take measurements of how Mars formed, how Mars is evolving over time. So again, yeah, very important to get that out as quickly as possible.
Right. So there are 3 main instruments on InSight. One is a seismometer, essentially. So it's going to sense Mars quakes, and that'll tell us about you know, how Mars formed. It will tell us, you know, why on Earth do we have you know, so much plate action, and Earth, you know, rotates, kind of moves underground, and new Earth evolves to the surface, etc. And that doesn't happen on Mars. So is that because of our thick atmosphere, or, you know, exactly how did all that work, and why is it the way it is today? So that will really help us understand Earth better, and really our whole formation of the solar system.
Yeah, in the solar system, we have terrestrial planets and we have gas planets. You know, you have the gas planets like Jupiter and Saturn, but then we have terrestrial planets, rocky planets like Mars and Earth and Venus and Mercury, and protoplanets like Pluto. And especially Mars, Venus, and Earth are pretty close together. And it's interesting to know why Earth has the tectonic activities, has the plates shifting around it. And there's some theories about if Mars used to have that before. And the Mars quakes will allow us to take measurements of some key items below the surface of Mars, like the temperature, understanding what kind of frequency the tectonic activities, Mars quakes are happening, which will help us model what's happening inside Mars. And that will, of course, as Michelle said, help us understand what's happening here on Earth as well.
Right. The other one of the other instruments I find really fascinating is called the HP3, and it's going to drill down 5 meters and sense the heat inside Mars and tell us more about the core. So that's really exciting.
And I think people call it the mole too.
The mole, yeah, that's pretty funny. I'm really interested in it because it will tell us, at least in one spot, the characteristics of the dirt and the soil there, which we need for that modeling I was talking about to understand how the engine plumes will disturb the surface. Now, it won't tell us everything about every place because Mars is so diverse in its surface characteristics, but it will at least give us one data point.
And actually, the very next picture, I think, is a little bit showing the picture of what that instrument kind of looks like. I think it's, click around that.
Click around.
Maybe. It's showing up there as next slide, at least. Well, we'll get that up, but at least, yeah, there you go. So you could, it's a visualization here, but you could kind of see the 3 instruments actually are all up there. You could see SEIS is this little dome-shaped thing that seismometer that Michelle was talking about. I think that's HP3 right there.
Right. We are not landing on the edge of a cliff. That's just a visualization.
Yeah, that's true. This is visualization.
And those are the size instrument is actually deployed by a 2.4 meter arm on InSight. So, you know, relative to the size of the lander, it's got a pretty long arm on it. And we're going to actually use the camera to look around the landing site and see what kind of disturbances we caused as well.
Absolutely. So it's going to be pretty essential type of measurements that those 2 instruments are taking. And you mentioned there's another instrument on board.
Yeah, I think it's a sounder. Is it
the RISE
yes.
antenna?
Mm-hmm.
Actually, can we go to we'll go to the next picture. I think we can see a little bit more cleaner picture of the instruments. There's SEIS and there's HP3. So the RISE antenna is an antenna. So it's basically taking measurements of how Mars is oriented. And effectively, that's allowing us to, again, take another geological measurement of Mars to understand if, the spin of the planet, whatnot, how that those are key essential ingredients for the modeling of the geology of Mars.
Right.
And so that's the 3rd instrument on here. It's kind of harder to see in this picture, but it's part of the package that's on top of the lander. So those are your 3 main instruments. And actually, I think it's kind of cool that even though this is a NASA mission, we have a lot of collaboration from outside America in these. Isn't that right?
Yes, I think HP3 is a European-built instrument, and there are many components that we have on the landers, particularly when we fly instruments that are contributed from other countries. So that's really exciting, and it's very nice collaboration. We build relationships with engineers in other countries and scientists, so it's really an international endeavor whenever we send something to Mars.
Absolutely. And actually SEIS itself is, I think the principal investigator is French as well, I believe so. So, even though this is a NASA mission, we really are representing the world when we do these missions. And this has been true for some of the other Mars missions that we have landed and are working on. I'm working on Mars 2020, which will incidentally launch in 2020 and land there in 2021. And that's the next up mission. I have to mention that since that is another one of my projects. And that mission also has a lot of foreign contributors to the instrument. So NASA always looks for that as well.
That's right. And so should we go to some of the questions
Yeah,
that
let's
we've
do that.
received
Let's do that.
ahead of time? I've got them printed out here. So I'll be looking down a little bit as we go through these. I guess while we're on the subject of science, there's a question about if InSight will detect past life or current life. And there are no instruments on InSight that are looking for life, but I think as we've described, this understanding of the Martian planet, how it evolved differently than Earth, and what are the similarities? How did our solar system form? I think are all keys to putting the puzzle together about life on Mars. So even though InSight doesn't have any life detection science per se, it really adds to our whole body of knowledge.
Yeah, and on Earth, this is the only planet we know of right now where we have life. We always try to compare to Earth when we go to another planet. So it's trying to understand how Mars's geology is with respect to Earth, because we know when there are tectonic activities on Earth, when there are certain type of features on Earth, life exists there. So we're trying to, in that sense, understand it, but nothing to directly detect life. Although there are some other missions planned and have been, as you mentioned, Phoenix was looking for ice, which is basically InSight 10 years ago in shape. So we have used similar spacecraft to look for signs of water, signs of carbon, which are basically signs of life.
Mm-hmm. So one of our questions here is, what's the next step? So Sam, you started to talk a little bit about Mars 2020. Mars 2020 is actually going to collect samples of rocks and cache them or put them in containers on the surface so that we can return them later to a laboratory on Earth. And that's really the mission that's going to set us on the life detection path. If we bring the samples back to Earth, then we can keep those samples for years and years. And as our laboratory technologies evolve, we may get more sophisticated instruments that can allow us to do that life detection job even better than what we could send all the way to Mars. So we're very excited about Mars 2020 and what's to come after it.
And I mean, we did the same thing with moon rocks, right? We took moon rocks in the late 60s, early 70s, and we're still looking at them for life or whatever you want to talk about, any kind of minerals on them. And that's kind of the same idea here with Mars rocks, because I think a geologist on Earth can do so much more with that sample than what a robotic mission could do just by itself on Mars. So the idea is to bring it back. So it's part of a two mission architecture. So Mars 2020 and the mission that I'm working on is launching in, I hope so, is launching in 2020. We're planning on, we actually just figured out where we're landing there at a place called Jezero Crater. So take a look at that on nasa.gov. And it's a river delta. The idea is at river deltas, there's usually life. And so we're going to take samples there, and another rover and a lander in the later 2020s will go there and grab those samples and bring them back to Earth. That's the idea behind that.
Yep, and all in preparation for sending humans.
Oh yeah, ultimately the best way to look at any of this is to send humans there. I mean, I would love to go there too.
Let's see, one of our other questions is how long will Mars InSight operate and how long will it stay there? So we'll stay there forever, but it will operate for about 1 Martian year, which is about 2 Mars years. Since Mars is farther from the sun than the Earth, it takes about twice the amount of time for Mars to revolve around the sun in its orbit. So about a year, but another question deals with, is there a possibility for an extended mission? We always luckily tend to over-engineer our vehicles. So we plan, I think, to keep InSight operating as long as it is still working. I think the limitation, as is usually the case with the solar panel powered missions, is, you know, how your cell phone battery wears out after charging and discharging many times. That's what will happen with InSight's batteries after a while. So at some point, it will not charge up enough to stay warm and operate, but we hope that's way beyond our design lifetime of one Martian year.
And I mean, the Opportunity rover is still technically on Mars. The Opportunity rover, another one of the NASA missions that thankfully successfully landed on Mars, landed in 2004, and it's still operating. It had a twin, Spirit, that stopped operating a few years ago because it had mechanical wear. So it basically kind of depends on, after you go beyond the time frame of the initial mission, how your mechanism's holding up to Mars. Mars is a pretty harsh place to land, even though, you know, we're sending all these robots there and we're designing it to last longer. At some point or another, Mars is going to catch up to us. So Opportunity has been pretty lucky. Spirit, you know, lasted well beyond its main mission. But eventually it succumbed, and we're hoping to operate InSight as long as possible. But as you said, 2 years, 2 Earth years.
Yeah, so there's a lot of questions here also about humans. So I hope we've shown you, and you can see from the pictures, that humans will not be on InSight. This is a robot, as have all of our Mars missions been. But we talked about 2020 and then returning a sample from Mars. And one of the things we're working on here at Langley and at other NASA centers across the country is how will we send humans to Mars, and what will that look like? How will we do the entry, descent, and landing portion? Because obviously that's very critical part of the mission, get all those things safely down, particularly the crew. And then it will be you know, one of the first times that we send things back from Mars. So we want the humans to be able to come back home to Earth. And that's what's really very important about the Mars sample return mission as well, is demonstrating that round trip. And actually launching a rocket remotely from another planet. I think that's just fascinating that we're going to try to do that. So lots of challenges, but we're working on technologies at Langley and at other places around the country to help us land humans on Mars. Hopefully, you know, late 2030s or so. We're sending robots and humans back to the moon, and we like to say forward to the moon, as a stepping stone and a way to practice and get some experience with humans living beyond space station, in preparation for sending them out to Mars and other distant places. So we've got a long way to go, a lot of challenges, but we really are making a lot of progress on the technologies. And really, it's our middle school audience out there that will be the engineers sitting in these chairs when we finally do that.
Absolutely. Well, I hope to see that before I retire, for sure. Actually, looking at InSight and kind of piggybacking on a little bit of the conversation that Michelle was saying, you saw in the video that we showed before that InSight uses a big parachute to slow down. That parachute actually opens up supersonically, faster than the speed of sound. And those parachutes were really first designed in the 1970s for the Viking mission, which Langley actually spearheaded 2 landers. They were the first 2 landers to successfully land on Mars. There were 2 NASA missions in the 1970s. And that parachute design has kind of stuck around since then. They work really well. They have worked successfully 7 other times, and InSight's using them too. But really, that parachute is getting to a limit of its size. We can't keep making it bigger and bigger. And for human missions, we're talking about bringing down way more mass than what we're doing right now. So that's kind of the idea, to develop technologies that Langley and other centers are doing to make sure that we can land on Mars without keep resorting to using a supersonic parachute.
Absolutely. Let's see, we got a couple other questions, and then we'll go to some of the ones we're getting real time. Let's see. The surface of Mars looks like Earth because of canyons and valleys, so why can't we live there? And Sam, you talked a little bit about how harsh it is on Mars. Mars is much, much colder than Earth. And
it's colder than Antarctica, actually, if you think about that.
Yep. And the atmosphere is about 1/100th the density of that on Earth. And so we wouldn't be able to breathe there unless we're in a suit or in a closed environment.
It's also carbon dioxide.
It's also carbon dioxide,
Yeah.
yes. So, one of the other things people were wondering about is when we send humans, how will they live without oxygen, without our, air, atmosphere, nitrogen, and oxygen? And one of the important things about InSight and how all these missions tie together is really understanding the Mars environment, understanding how we can live off the land when we send humans there. Because when you go camping, you don't take, everything you own with you. You build a fire from, trees in the woods, and you get your water from a stream if it's safe. And so we're going to do the same thing when we send humans to Mars. We call that in situ resource utilization, so using the resources that are there. So that's why understanding about the atmosphere and the environment and the soil and the characteristics of the planet is so important before we send a crew there. So there are a couple different types of ISRU. One is taking in Mars carbon dioxide atmosphere and processing it into oxygen and water for use by the crew. And then another is actually digging up the soil and processing it by heating it and then taking off the gases that are extracted. And that's another thing that operating at the moon will give us practice with, because if we have companies starting to use resources there and we want to send humans, we're going to have to do the same kinds of things and develop the same sorts of technologies to give us practice for Mars. And so when we send humans, we'll live off the land as much as possible. That air or regolith extraction will also allow us to make propellant for the rocket that will take the humans off the surface and back to Earth, because we don't want to take all that fuel with us.
Yeah.
It's too heavy and too expensive. So, lots of different technologies are going to be needed to support crews on the surface.
And another thing to add to that, which the lunar missions will definitely help us to, and it's also true for Mars, is radiation shielding. So on Earth, we really benefit from our magnetic field that's protecting us from most of harmful cosmic radiation that's out there. I mean, that's dangerous to your body, dangerous to any kind of living organism, because those cosmic radiations can alter your DNA. And so when we go to Mars, Mars does not have a planet-wide magnetic field. It does have localized places where there's some magnetic fields, but it's not at all anything like Earth. And of course, Moon doesn't really benefit from that either. So being able to test out technologies that help us protect from that cosmic radiation is useful for trying it out at the Moon, which is close by, and then taking it to Mars. That's extremely important to taking humans there, because even if we send humans there, they're staying on the surface for a while before they can come back, because of that 2-year alignment that Michelle talked about before, that it takes 2 years, about 26 months to align the trajectory between Earth and Mars. So, you go to Mars, you can't just come back immediately. You have to wait for that trajectory to align again in order to come back to Earth.
Speaking of orbits, we have a question we were fighting over. I'll let you have it. We're learning about ellipses and hyperbolas. Can you tell us how those apply to space travel?
So I think if you don't know about Kepler's laws, again, I would suggest looking it up on nasa.gov. But really, Kepler, this mathematician, came up with a lot of the equations that we use today for doing planetary missions, trying to figure out the trajectories between different planets. And one of the things we figured out since him and through other mathematicians like Isaac Newton is that the trajectories that we take are all some form of a hyperbola or ellipse or circular shapes. These are called orbits. So we're orbiting some sort of gravitational potential. So usually when you're in the solar system, you're orbiting the sun. When you're just orbiting the Earth, the gravitational potential is Earth. So those shapes that the spacecraft makes around Earth, around sun, as it's going from one place to another, are these ellipses and hyperbolas. And I think you mentioned that kind of got you into this field, right, Michelle?
Yes, when I majored in aerospace engineering, I had to choose between aircraft and space. And when I took my first orbital mechanics class and learned about Kepler and the geometric shapes and the orbits, that's what got me hooked on space for sure. So it was really pretty exciting. And all those equations can be solved by hand. You don't need a computer, just a calculator or a piece of paper. So I think that's a really cool, application of geometry.
And you saw the ellipses don't really go away, because when we talk about our landing performance on the ground, we're talking about our landing footprint ellipses. So yet again, it shows up there too.
That's right. But I think Adeline has some real-time questions for us as well.
Yes, so now we're going to ask some questions that you have been asking in the chat. So our first question is, what are the wind tunnel models made out of?
Oh, this is all 3D printed items. So yeah, actually, Michelle can show it to you. So they're a little bit rough, but actually that's fine, because the scale of the roughness that the 3D printer creates is nowhere close to the kind of surface roughness that the real vehicle's properties are calculated with a metric called Reynolds number, which kind of shows you what kind of surface roughness and what kind of aerodynamic properties you can have. And so this is a 3D printed model, and we were able to test it in relevant conditions that they're going to see on Mars.
Again, Tom mentioned a couple times that this was a pretty simple wind tunnel test. These models, as many of you know, you probably have 3D printers at your school or at home, or know someone who has one. These are very inexpensive to make, and once you have a computer image or CAD drawing, computer-aided design drawing, you can make these in a few hours, and they're very low cost. So that helps us do our wind tunnels very cost effectively.
Yeah, and this is becoming kind of the norm. Another project that I worked on, we wanted to see how it's actually flying. So this was a static test, right? I told you guys that it was kind of fixed in one area. We wanted to see how this other vehicle interacts as it's flying. Now, it's kind of hard to test something flying at full scale all the time, but we were able to shrink down the model and test it in one of our wind tunnels here at Langley called a vertical spin tunnel, where we really spun it up and let it fly. It's kind of like one of those indoor skydiving places that you guys might be familiar with. It's a little bit more sophisticated than that. We have cameras around to take pictures of where the model is going so that we can understand the forces and moments on it. But again, it was a 3D printed model, pretty simple. We were able to take the CAD, computer-aided design model, print it, and stick it into the wind tunnel, and very quickly figure out what the drag coefficient of the vehicle was.
And that works as long as the wind is low speed. When we get to hypersonic velocities, like you saw when the capsule first enters the atmosphere, those have to be made of metal, because the flow is very hot and the model gets hot.
That's true.
Our next question is, where on the West Coast did InSight launch?
Vandenberg Air Force Base, so that's slightly outside of Santa Barbara.
And do we expect more launches to come from the West Coast?
That's a difficult question. I know Mars 2020 is not launching from there. It's launching from Kennedy Space Center.
Yeah, I don't know of any NASA mission, Mars missions. There are many, hundreds of NASA missions. A lot of them are for observing the Earth. And so I think some of them go from Vandenberg because they're usually going into polar orbits, and the satellites are small. As we talked about, Phoenix being InSight being a little smaller than some of the other Mars missions. So it just really kind of depends on the size rocket that you need for the payload or the satellite that you're putting up and where it's going. But I don't know of any Mars missions that are planned to launch from Vandenberg.
No, yeah.
Our next question is about the Mars CubeSats, and they want to know if those will be interacting with InSight at all, or how those relate to InSight.
They've been, first of all, Marco is 2 CubeSats, and they're the first, what we call planetary CubeSats. So the first ones that have really gone out beyond Earth orbit. And that's exciting in itself, because think about the great science we could do on other planets with really small, affordable spacecraft that have been built by, high schools, middle schools. Really anybody almost can put one of those together if they have the right parts. So that's going to open up a whole new field for us. But Marco is kind of following InSight on its way to Mars, and it will send back some data, communicate with InSight, and then as InSight lands, enters the atmosphere and lands, Marco CubeSats will go on by Mars and just keep going out into sun-centered space. And so their job is over after they communicate and send data back from InSight.
One cool observation about the Marco spacecraft, I was talking to one of my colleagues who's actually at JPL right now in the control room for InSight. She was mentioning that we do these trajectory correction maneuvers, TCMs, on our main spacecraft. So InSight absolutely did some of these TCMs on the way there. And that's to make sure when we first launch, we don't really aim exactly for our target. We aim slightly away from it and then do these trajectory correction maneuvers, some of them planned to make sure that we are hitting the target, and then some of them are contingent, where if we see any errors in our trajectories, we can fix that along the way. So we do these TCMs on our normal spacecrafts. Well, these CubeSats, these are tiny. They themselves have to do these correction maneuvers too, so that they can stay in the same alignment with InSight and Earth. So it's kind of interesting that this is a tiny little spacecraft, but it's doing the same kind of maneuvers that this larger spacecraft has to do.
Now we have two final questions. Our first one is, do we know about how much it cost for us to be able to build and launch InSight?
Oh, that's definitely a Michelle question.
Oh dear. I know that the mission was originally proposed to be less than $425 million. That's the Discovery class cost cap. So for planetary science missions, we have kind of three categories. One is called Discovery, 425 million or less, without the launch vehicle and operations. And then we have a class called New Frontiers, which is up to almost $1 billion. And then the flagship class missions are typically over $1 billion. So those are like Mars Science Laboratory and Mars 2020. Discovery and New Frontiers are all competed missions. So organizations write proposals and then they're selected as time goes on. So as we said, with InSight, it was proposed in 2010, got selected in 2012, and then it becomes a real project that NASA manages, but it's executed by the organization that proposed it. So there were some difficulties with the instruments, as we mentioned. So I actually don't have the total cost as it's tallied up today. But you have to factor the launch vehicle and the operations in there on top of that original $425 million number.
And then our final question is, about how long will we have to wait after InSight has landed on Mars to know that it has successfully landed?
That's a good question. I read that the communication delay right now, due to the distance between the two planets, is about 8 minutes and 7 seconds. So it will definitely be 8 minutes and 7 seconds, which is crazy to think about, because InSight will have landed before we know. We'll still be thinking it's at the top of the atmosphere. So we're not even there yet.
7 minutes of terror and 8 minutes of delay.
Exactly. So it will likely be at least 8 minutes, probably a little longer before we get that first signal back. And I don't believe it will be a picture. It will be something a lot more simple.
Yeah, the Marco CubeSats that we talked about would help us a little bit, because they're acting as transmitter relays between InSight and Earth. But we don't have that real-time feedback. We actually had it for our past lander, Mars Science Laboratory, that landed on Mars in 2012, but we don't quite have the same type of orientation and satellites to give us that real-time feedback. So we'll get tones, I believe, but that's about it.
Right. So we'll say, we'll hear InSight say, I've hit the atmosphere and my parachute has deployed and maybe my heat shield has deployed and my engines are on. Of course, we'll find that out a little later because of the time delay. But so it will be probably 10 to 15 minutes before we have an indication that it's down safely.
But if you're watching the real-time video of the landing day, which will be happening this afternoon, you will hear the engineers who are narrating it will give you that feedback typically.
Yep.
Well, I would just like to thank you both for giving us all of this wonderful information about Mars InSight. We are now going to put some links up on the screen for you so that you can see a little bit more information, and we are going to transition to our classroom activities so you can see what you could do in the classroom to sort of be with Mars InSight with us this afternoon.
Thank you.
Thank you. Okay. One more.
Hi, welcome back, and thank you for watching with us. We're now going to show you a brief overview of an activity that you could do in the classroom with basic classroom materials. So this does not require anything special. These are all things you probably have laying around your room or even at home laying around at house. But first, this is a robotic arm challenge. And so robotic arms are something that are really important to NASA. They're something that have been on all of our landers and rovers that we have sent to Mars. So here you have some examples of some arms. We have InSight's arm, which will be positioning all of the seismographs and all the instruments. You can see both Spirit and Curiosity's arms, and eventually Mars 2020's arm. So for this challenge, students will use the Engineering Design Challenge to design, build, and operate a model robotic arm that will pick up objects from one location and drop them in another location, which is exactly what Mars InSight is doing. Its robotic arm will pick up a instrument from one part of the lander and set it down on another. So here's a few examples of materials you could use. We have a variety of different materials out in front of us, but the possibilities are endless. Whatever you can find is what you can use, or whatever your teacher tells you you can use is what you can use. So to set up for this activity, you would use a table and some bowls and objects and tape. You would first put a piece of tape down at the 30-centimeter mark, a second piece of tape down at the 60-centimeter mark, and a third piece of tape down at the 70-centimeter mark. Now, at the 60-centimeter mark, you're going to put the first bowl of objects, and that's what the robotic arm is going to be picking them up from. And the second bowl will be at the 70-centimeter mark, and that's where you're going to be dropping them off from. Now, we're going to talk about the engineering design process. So first, you're going to identify your problem, which we've already told you. We identified it for you. You're going to design, build, and operate a model robotic arm. You're then going to brainstorm solutions. So this is where you're going to take some paper, you're going to draw your designs. This is where you want to draw multiple designs so that you can eventually decide which one is the best one and which one you're actually going to build. Then you're going to select your design. You're then going to take all of your materials and you're going to actually build it. So this might not be what you end up being your final end result, but it's important that you start creating something, see what happens with your test and evaluate stage. And then from there, you'll know what you need to change. And then you can optimize your design and eventually share your solution with the class. So in front of us, we have a bowl of objects that you can see. So this is just some random objects that we found in our office that if we were doing the activity here, we would use. So we have some balls, we have some little canisters, some wheels. Your objects can be anything. And then if we were to do the activity, we might use some pipe cleaners. We have different types of string. We have lots of different types of tape. You're definitely going to need a ruler because you need to decide how long your arm has to be in order to pick it up and move it to another object, and that distance. So you might make an arm, but is it the correct distance that's going to be able to get it from one bowl to another? And also, your bowls might be different sizes. So the bowl that you're picking your objects up from is going to be different than the bowl you're dropping them off into. And so those are all important things you're going to have to take account when you create your arm. So good luck. Hopefully you can do this activity either in your class or at home and share your results with us. Let us know how it worked for you at home. And don't forget to watch InSight later this afternoon, Land on Mars. This is a huge event and it's definitely something you're not going to want to miss. Thank you.